Hi, and welcome to this week's episode of the Structural Engineering Podcast with Max and Zach. This week, we talk with Bob Johnson, a Chicago native and distinguished structural engineer that designed part of the Chicago Skyline. Bob is also a huge advocate of teaching STEM to children. Bob can be found on LinkedIn and Twitter at the Engineering Guy SE. To learn more about Bob and what he's doing to promote structural engineering, search Bob Johnson STEM on Google. Now let's get into this week's episode.
My name's Bob Johnson. I was kind of not groomed, but parents, especially grandparents, kind of steered me to engineering. I graduated high school in '65 from if I may say so, a famed high school in the city. I like to brag about it because not the physical building, but the original play was about that high school.
And that's so cool.
Yours truly was not a greaser. Okay, then I went to, I was steered to college, IIT, Institute of Technology in Chicago, bachelor's in '69. And when I was interning, my first job was engineering job was in '67 at an engineering firm, big engineering firm, architectural engineering firm in Chicago, Halliburton Root. And then the '68, I interned at another big architectural engineering firm, Skidmore, Owens and Merrill. And when they were doing
a big one.
Yeah, and they were doing the Hancock building, even though I didn't get to work on it, they were doing it. And I kind of got the impression with talking with the engineers, if I wanted to really stay with engineering, I had to go for my master's.
Yep.
So I went back to school and got my master's in '71 from IIT. In '70 and '71, I heard about another engineering firm called Alfred Benish. They're really big in Chicago, but they are strictly a structural civil firm. And it was good that I linked up with them because I wasn't aware that there's these consultants that work with the architects. And in '71, I joined the firm full time. And for the next 25 years, I worked in their building department.
When you started Alfred Benish, what did they start engineers with in the '70s? Like what is the first project?
They gave me the responsibility of doing flat slab design. At Harbor Point, I did the typical floors.
Wow.
And back then, the flat slab, I don't know if you ever heard of ADOS.
No.
That was a canned program that Benish and I believe the Portland Cement Association wrote for mainframe computers. At Benish, they were one of the first ones to have a IBM 360 mainframe computer. And a couple of the key basic programs were the flat slab program, and they had a engineer, and I don't know if you ever heard of Dr. Shankar Nair. He was really big in the city, and he wrote our internal lateral shear wall analysis program for the mainframe.
Wow.
You use, at that time, you ever heard of Stress? Stress was the other, big analysis program back in the '60s, early '70s. And then we had another one the Benish people and our president wrote, we called it the column stack program, which you gave the computer the floor tributary area, the concrete strength, the number of floors, and the computer popped out the rebar.
Wow.
It was so sophisticated. We could take the computer output and make copies of it, output, and paste it on a drawing, send it to the printer, and that became your column schedule.
It was that good?
Yeah, it was that good. Yeah,
we barely do that now.
Yeah, it was about 15 years later, in the early '80s, the president and of the firm who had wrote the program came to me and says, Bob, the program designs the columns and just basically gives you the rebar you need based on certain parameters that you gave it in terms of strength, size, and shape. You had to, do an iterative technique in terms of finding what was your concrete and your shape to get it to work. He says, let's take a close look at this. Can you make it more sophisticated? You got any ideas? And I said, well, what controls the design of columns? Your shape, your rebar, your concrete strength. So we put those variables into a really sophisticated program, and we let
this is like 85-ish, right?
About 80, about 83, 84, in that time frame. You gave it three parameters: the shape, a rectangle, which you fixed one side, a square. You just told it the square, and then round. And then the other big variable is the concrete strength. And you gave it, decided to set it at 5 concrete strengths. So back then we did, 4, 5, 6, 7,500, and 9.
Oh, wow.
And you gave those variables to the program. And what does it do? It designs 75 different columns and picks out the best round, the best square, and the best rectangle.
It makes me feel like we haven't come anywhere in 50 years.
And what I got, the program, the first time I used it was on a building, and the building had already been designed. It was just starting foundation work, and the contractor or the owner developer says, "Can't we save some money?" The usual. Too much money. So I says, "I've got this new program. We're going to test it. Do you mind?" He says, "No." So we tested the program versus the actual design that was already on the boards and they were constructing from.
Mm-hmm.
And we found out we had a problem. We were wasting money like crazy.
Oh, no.
So I went in and presented it to the owner. We actually had a big meeting with the owner, the developer, the contractor, and the architect. And this is what we came up with. Use the highest strength concrete, the 9,000 was optimal. You could have probably gone to 11, but turned out the 9 for costing purposes was the best. So use the 9 as much as you can. Use round columns as much as you can, because the round column
area
is because of the formwork.
Okay.
And this is the other one, your structural for all the engineers out there. We found out the optimum reinforcing was 0.75%. Now, if you remember in the code, you're allowed to go under 1%, but you can't use the concrete for under 1%.
Mm-hmm.
So there's a way to tweak it. So long as you can design a column with 1%, even though it's 0.75 with that area, you can use it. Don't go over 1.5% steel. In fact, try to stick around 1.33. Why? We're building a concrete building. We're not building a steel building. So we gave all the data to the contractor and says, we think we can save you $300,000. He comes back, and the architect comes back and says, Bob, this is a Mies van der Rohe building. You can't put round columns on a square building. The contractor says, how big are your columns? I said, they're this size. He says, are you aware if I put drywall cladding around the round column, I'll give you the square column that you want. Well, what's that going to cost me? It'll cost you some bucks, but give me the number. He says, we can save you $250,000. It'll cost you $50,000 for the drywall. So as they're coming up, we totally changed the design to use round columns wherever possible.
Way.
And then
drywall around.
drywall around it, and don't go over 1.5% steel. I mean, I see these buildings going up, and I'm seeing all the steel. I can see it in an earthquake zone. But if you're designing gravity columns, you're building a concrete column. You're not building a steel column. It was a shame we didn't get to use that program very much farther along because there were certain buildings. How should I put it? I think we used it on 900 North, but columns had to be rectilinear.
Yeah.
that one. But we did follow the dictive or whatever, use the highest strength concrete that's economically feasible. And at that time, it was 9,000, and keep the steel down to 1%.
Jeez. I'm amazed at the amount of computer use at the time. Was that typical, or is that
It was all on
Benesh? That's
no. The classic is Sears Tower was done. I don't know which program they would have used, if they probably used Stress. But at that time, another great story with the buildings that we were doing, the shear wall type buildings, it took forever for the computer to crunch the numbers. So what did we do? At 6:00 at night, they put the deck of cards into the computer, and it read. You were familiar with punch cards?
Yep. Well, okay. I've heard of them.
The deck in the computer, and let it run all night. And then you come in the morning at 6:00 or 8:00 in the morning and find out that the computer had finished the program. And then you found out, oops, we had a punch card, error or whatever. You couldn't tie up the computer during the day because you were doing other programming aspects. So then it was fix the deck and then do it again the next
night.
But that was all done on mainframe computers. Our competition had also, I don't know what Skidmore-Owens and Merrill had for their mainframe, and I don't know what a predecessor in Chicago. You've heard of Thornton Tomasetti,
of course.
They bought out a firm here in Chicago called Cohen Barreto Machertis, CBM. They were one of our big competitors. And I'm almost guaranteed they had their own frame, whether it was probably an IBM 360, to do the big calculations. Back in the 70s, everything was done for the staff engineers by slide rule. And then I can remember too the big issue. It was about 73, 74. When the first 4-banger calculators came out.
Oh, man.
The big discussion. Okay, the first one I think was called the Bomar Brain. It was just a 4-banger. Add, subtract, multiply, and divide.
Yeah.
It was about 73, I think, 74. The two competing calculators were Texas Instrument, and they had the scientific functions in there, sines, cosines. And the other big competitor, and of course you've heard of them, was Hewlett-Packard.
Of course.
And their first generation big calculator was the HP 35, and then the really big one was their famous HP 45.
How much were these?
Okay, you want another great story?
Yeah.
Okay, we were back at Benesh, and I don't know what the other firms did, but Benesh says, okay, we got to go calculator. So we're going to have a special deal for the employees. We'll subsidize the purchase of a calculator for you, 50-50. You got two choices. The Texas Instrument, which was $150, and the Hewlett-Packard, you ready for this, was $400.
Wow.
Okay, now you ask yourself, why the difference?
Yeah.
The Hewlett-Packard operated, you're familiar with the RPN technology?
Reverse Polish notation? Yeah, of course.
And TI was with the quote Dan sign.
Well, I can't do RPNs.
And the other big issue was the Texas Instruments were a lot cheaper because they were built cheaper. Numbers on there were painted on.
Wear down eventually.
Hewlett-Packard decided we're going to be better because that paint's going to wear off. The key, I don't know if you know it, but the key itself is two processes. The number is actually a separate casting, or and the letter. The more you push on it, all you do is expose more of the separate casting. So it was the strangest thing. The drafters at Benesh, for whatever reason, money wise, to go with the Hewlett-Packard. Money, and the engineers went for the TI. I took a look at the way the machines were built, and also the reverse Polish notation. aspect.
Mm-hmm.
That the reverse Polish notation is way ahead of the TI.
Yeah.
Especially for the storage automatic storage stacking of numbers.
Mm-hmm.
So, and then the first generation calculators, they ate up batteries. So everybody had them hooked up to the portable charger.
Okay, yeah, they could just be plugged in.
Plugged in.
You could take it out if you.
The problem we had with that, and let's see if I can do it with the mouse. Okay, you had your calculator hooked up to the power cord here, and you're moving the calculator around on it. What did you wind up doing?
Breaking that thing right up.
Breaking the wire in.
Yep.
Every 3 or 4 years, you had to get a new charger, and it turned out that the first generation TIs went bye-bye because of various issues, and the Hewlett-Packard 45 was a workhorse, and I still got mine, even though eventually, the sensor and the key, they finally went by the wayside. And then you got your second, third, and fourth generation calculators that had the built-in programming capabilities.
Mm-hmm. Oh, that's cool.
And the other thing, then in the late 80s, the big debate for the people out there is we started to bring in CAD.
Yeah, when did you get computers at your desks? Was that when CAD came in?
That was in the early 90s, but let me start with the CAD.
Yeah.
The big debate was in about, I don't know, was it 1988? There were two competing CAD systems. One was, I think, called Computer Vision, and the other one, I think, was called Prime Medusa or whatever. These were dedicated CAD systems where you bought the whole mainframe and then your desktop or whatever. And the big debate became which one to buy. And I can't remember which one we bought. I think we bought Prime. And we only had the mainframe and a couple of workstations, and that was it. Then, as you know, Windows started in, was it about 83 or 84 with Windows 3 or whatever.
Mm-hmm.
By the late 80s, people started writing programs for Windows. And that really shook up the industry with regards to all the dedicated
machines, like one task.
Yeah, before Microsoft Word, you had dedicated word processors too. But in about 80, I don't know, was it 89, 90 or whatever, now we got the two competing systems, AutoCAD and Intergraph MicroStation. Well, what happened was in Illinois, for the big debate in Illinois was which one to use for state work. In our state department, IDOT, decreed they wanted the work done by Intergraph MicroStation. So all the firms like Benesch, which was heavily skewed to transportation and bridge design, was forced to do Intergraph MicroStation. And the architects went with AutoCAD. One of the last firms I worked with, our tech guy would take the AutoCAD and convert it over to MicroStation because he liked working in MicroStation. He just thought it was a better product.
Huh.
And then when he had to give the drawings back to the architect, there's a processor to convert it from the MicroStation back to the AutoCAD.
Wow.
But the engineering firms used MicroStation. The other issue we had is now in the early 90s, we had all these people working on dedicated programs for Windows. And you probably know them, Ramsteel.
Oh, yeah.
Yeah, it was not. I still remember the project because we had in 1993 we were working on McCormick Place. Project lead decreed we want the building designed using Ramsteel. We don't want any hand calculator or any other stuff. We were forced to purchase Ramsteel, and I got to work on one of the earliest versions of Ramsteel and was in contact with, I think his name is Bergsma, but with the guys that wrote the program. Because
is that a U.S. program? Or he's somewhere fun, right? It was like...
I can't remember where he's with now, but I can't remember what the original firm wrote the program. and I running the program for McCormick Place. I was, yours truly, if I may toot my own horn a little bit, was finding some of the bugs in the program because we were really taxing it because of the curvature of the building. It was eating up a tremendous amount of memory. It was not on a regular grid system. We were able to put in a radius, still with linear beams, but as the curvature, it had to generate additional grids, and it ate up a tremendous amount of. And because of that, the program would crash because it was eating up too much memory. We had to then break up the building, and also there was other issues that we did not discovered, but it was just part of the program. Is because of the curvature and how the deck hit the beams, control how it spaced the studs. It was, because of that skewness, it said you could only fit 6 studs on the beam. No, we can cut out the studs. And there were a few other, issues that we discovered, but by, over the years now, that program, starting off in about 93 or whatever, they added all the additional
all these modules,
and then the frame.
Yeah,
I was truly got to use that program back in 93 on, and again, when that program, even though it was on a laptop, it still took about 5 minutes to run a floor design.
Yeah.
Was, a little bit later when the processors, we went from this. I don't know if what we had on the processors in the laptops, if we were up to 486s, and then I can't remember all the names. The laptops, it's just for now. You just hit the key and
goes.
I've been away from main hard structural design for at least 10, maybe 15 years.
Yeah.
Newer programs that are come online, all the frame analysis programs, the way you can model structures, again, the way after you get with your engineering design, give the model to the contractor for the detailing, whether it's Revit or some of the other software going back from 1971 when I started, it's a whole world.
Yeah, I bet.
And then same thing with the younger engineers out there, how the curriculums must have changed in college, because it has to be now geared, you learn the basics.
Mm-hmm.
And how much they apply to, here's the basics. Now you got these computers that can crunch it. Because you're ready for this one in my, I think it was in my steel design course, analysis course. The teacher or the professor showed us all the graphic techniques that they used back 75, 100 years ago. So we were solving some of this stuff. He just showed us you could do this stuff graphically.
Yeah.
And in fact, that's how one of my colleagues showed me the book on building the Eiffel Tower. But a lot of that was done graphically.
Wow.
Just want to interject really quick. After the episode, we tried finding this book on the Eiffel Tower and found that there's many out there. If you've got your favorite, let us know. Now back to the episode.
When I had my bridge design course in probably 67 or 68, he was showing us how we can you design with rivets. I mean, how many people design?
Wow.
The stitch bolts are stitch plates. Because remember back at the turn of the century, all you had was angles, channels.
Yeah.
No I-beams and no wide flanges. So he was showing us how to design with channels, with the stitch plates, to stitch it together.
Yep.
They add angles.
And rivet and
then rivets.
Oh, wow. Was that completely out by the 60s, 70s?
Yeah, 60s.
Yeah, it's done. Way done. Yeah.
And then some of the one thing that I never took in college, I can't remember why, but I never took a course in post-tensioning. And then another course I had that never transpired. You ever heard of plastic design?
Well, not really. I could guess what that is.
Okay, 1970, I took a course in plastic design. And the way to explain it is when you build a steel structure, a lot of it is redundant.
Yeah.
Okay, you got a continuous beam or even a continuous frame. Well, let the thing go plastic. Let it form a, quote, plastic hinge.
Yeah.
It's still stable because it's redundant. So you can make your beams a lot smaller because they can, not a lot, but you can save 15% because you're letting them go plastic and you're not letting them
Stopping
fail.
at first yield. It's,
It goes to the first yield. So you got to control the yield, but you can, and for whatever reason,
he took off. Yeah.
A design solution to save, an extra 5, 10, 15%. But the key feature of the course was, how to analyze your structure to form the plastic hinges. And then so it doesn't create not additional hinges, such structure goes
unstable or, yeah. Wow. Curious. We had a question on, since we were kind of talking about software, right? I think right now you could probably throw a building together, draft, a few stories in a week, right? Really, really quickly. The buildings we're talking about here, what's the time frame like?
Well, I haven't. The thing is, you still got the issue with how complex the structures are. Mm-hmm. And think about it. The buildings that we're seeing now, like the twisted skyscrapers, and some of the other crazy structures that the architects are coming up, you could have never done that stuff 30, 40, 50 years ago.
Yeah.
And then the other issue we always seem to have is changes. Come up with your design. For whatever reason, you want to change this. The one aspect with regards to buildings, I didn't work on the building, but I went to lectures on it. One in Chicago in particular. I won't mention it by name, so I won't get into trouble. But the architect designs a 40-story or 50-story building, gives it to the engineer, designs it, and that's all designed. Everything's fine. All of a sudden, they start selling units in the building. We're selling a lot of units. Can we add a few more floors? So they give it to the engineer. Oh, yeah, we can add a few more floors. So now they got the model, and it's easy to add a few more floors. So that's one of the upsides. The downside is, we want to add a few more floors. Run it through the computer. We got a problem with lateral.
Ooh.
What can we do? Well, we really want these floors. Well, what can we do? Well, in this particular building, they were forced to add a damper.
Oh, no way.
So after they got a damper up there, as part of the original design, but they were able to give the architect a taller building. But again, we're going through all these iterations. Mm-hmm. Okay, for whatever reason, or the other one nowadays, a lot of times, unless you're working with the contractor up front, the contractor will say, I want to save some bucks. Can we change this? Can we change that? I want to do this.
Yeah.
I mean,
fair question, I guess.
I had a few buildings where, for whatever reason, we wanted to go with a flat slab, poured in place deck. Contractor says, I can save you money. Got to go on post-tensioned. In fact, I've got my own engineer that specializes in post-tensioning. So the building gets changed.
So would you say like the time in which it takes a building to be designed today is roughly the same as it used to take because of all the changes that are occurring throughout the process?
Probably. The other big change is when I started, I was on the boards, had the drawings in front of me, but was crunching numbers. I did some minor drafting, but I had draftsmen behind me doing all the drafting. And these guys were artisans. I mean, the way they drew stuff up, it was just amazing. Nowadays, how many are actually drafting nowadays? You have, hard drafter.
Not many.
So many of your engineers now are skilled with the AutoCAD or, like I said, MicroStation, or the like with RAM, the model that you built, and use that model for the
bring it in. Yep.
So I'm just wondering how many engineering firms have dedicated drafters. It's all they do is drafting.
I'll tell you, we have 2 to 25 engineers.
Back then, you had it's probably 1-to-1 because the engineer had a drafter doing his drafting. So that shows you how that's changed. And also, look how it's with regards to secretarial work. I mean, all the engineers have got a keyboard in front of them and type up their letters or all of that stuff. And if I may say so, not to for the people that are listening, not to be critical, but the drawings that we created, 30, 40 years ago had life to them. The drawings today, they're just flat. And again, how much they're teaching drafting techniques to the engineers producing the documents. In terms of key one is line weights and
it would never come up.
Yeah, no, line weights, and you don't have that capability necessarily with the. It's not sophisticated enough in terms of the way the computer operates to give you the almost three-dimensional effect. When you're cutting sections, so when you do a section, what you're actually cutting through is shown one way, and the stuff that's beyond is a lighter weight.
Did you have a drafting course in school? In college, were you?
I had 1 year. I mean, this is another thing that's changed, with regards to high school. I was on a curricular path to, become an engineer or knew I was going to be in science or technology. So I had 1 year in high school of mechanical drafting. Then when I went to college, I had 1 year of mechanical drafting in college. Basically, the first semester was the 1 year I had in high school. And then the second semester was a more of a sophisticated drafting course, how you can do stuff when you're doing three-dimensional stuff, even though it's two-dimensional, but I can't remember what it was called, descriptive geometry.
Ooh.
You'd create three-dimensional, how you analyze stuff two-dimensionally and create three-dimensional kind of things.
Yeah.
So all the engineers were required to have 1 year mechanical drafting, learning the skills of, lettering, line weights, cutting sections, and that's all now lost.
That's gone.
The young engineers now the skills in terms of computer technology is just phenomenal. But that particular aspect to me, I think, is lost.
What do you think is the thing that's changed the most in the 50 years you've been doing this?
Well, the key thing has to be computers.
Yeah, absolutely.
I mean, the structures that the architects are coming up with, it's just phenomenal. You could never analyze them. I don't know how you would analyze these twisted buildings. Or these fantastic cantilevers or hanging structures, or now all this net wall stuff. It's just amazing and exciting to see some of the structures that are being built. And I hate to say it, but I'm big on the internet, and I'm linked with a few key people in the Middle East or in China, and they're posting pictures of these buildings that they're building in the Middle East. Somebody just sent me the video on what do they call it? Yeah, they call it the horizontal skyscrapers. That's the like the Singapore building. Mm-hmm. And I had thought that Singapore building was one of a kind. No, there are several of these horizontal skyscrapers where you've got 3 or 4 towers, and then they connect the towers at the top with these horizontal skyscrapers.
Yeah, those must be just amazing. I feel like I have the Singapore one is by Arup. I have that in a book. I think
Arup is the engineer, but there's a famed. I I'm remiss. I know the engineers, but I don't know the
Of course. Well,
architect. But that's his signature style.
that's his move. Make the hardest thing to design, give it to an engineer.
Or also look at the one. I can't remember. It's the community. Their TV station in
Oh,
China.
CCTV.
Yeah, the one that go. Yeah.
Oh, that one is cool. Another Arab.
How would you have done that? 50. 50 years ago without computers and.
So something that intrigues me too. So you think with technology advancing so much, it's somewhat speeding up the process of engineering. Do you think we're losing skills that are still needed because of this advances in technology?
When you look back, like in Chicago, okay, my hometown, born, raised here. Look at our bridges. They're over 100 years old, and they're all riveted,
Right?
And all of that technology, the riveted stuff, and to keep those bridges still functioning. We just had one that was interesting. I don't know if you follow this, the story of it. It's our double-decker Bastille Bridge, and it needed to be repaired. It's the Wells Street Bridge, and that was over, let's see, I'm trying to think what year that's coming up on 100 years. That they had to replace a whole section of the bridge. And it's amazing. They got the original drawings and were able to mimic the original design. They found out, it's a double leaf Bastille Bridge, and they found out only a half of the leaf needed to be repaired. So they cut out that section of the bridge and then prefabricated a whole new section, floated it down the river, and then put it in and connected to the original bridge. And what's amazing is that since they had all the original documents, the bolt holes all lined up.
Perfect.
When they spliced it to the original bridge.
I think that was in. I was just looking through what I had.
Yeah.
I think it was in a Modern Steel. Yep. Not what I have here, but I'll have to.
The other big change for the people watching this is when I started out, and I went to a couple of lectures, of course, working at Skidmore and knowing the engineers at Skidmore and knowing the Chicago history. We had the Hancock Building opened up in about ⁻69. That was the tallest building in Chicago, with Fazler Khan working with Bruce Graham with the famous X-bracing exposed on the outside. And then in, I can't remember if it was 74, it actually physically opened, but I know in 72 it was under construction, was Sears Tower, now the Willis Tower, with the bundle tube with Fazler Khan. And those were steel buildings. And I went to a couple of lectures from Skidmore, Owens in Maryland. They were talking about the evolution, future buildings that will beat out Sears Tower. And they're talking about mega frame structures with big columns in the four corners and all steel buildings. And they kind of missed concrete, concrete shear walls, 5
old fashioned. Yeah.
At that time in the 70s, we were dealing with 6,000 pound concrete, I think, maybe 7,500. By the 80s, we were up to 9,000. In fact, I worked on one building where the contractor says, "Do you mind? I want to substitute our new experimental concrete. We want to see if we can deliver 14,000." And this was in 82. We want to deliver 14,000.
Wow.
And we talked amongst ourselves and said, what's the ramifications of just pouring, casting two columns at 14? You don't have to change. We're not going to change the rebar. We just want to make sure we can deliver 14,000.
And it was gravity only, right? Like, so no shear wall, no stiffness, yep.
Gravity only. So they cast the two columns at 14,000. They did their cylinders, checked it, and sure enough, after at that time, I don't know if if it's still got to be true. We had the 28-day break rule and the 56-day break rule.
Yep.
And at 56, it came up to the 14.
Huh.
And the material supplier then says, we can now, if you want, we can deliver
14,000.
14. Well, they walked it back. They pretty much started using 11.
Yeah. Was the 11 the 14 mix or something close to it? Was that the statistically as good as?
How they goosed up the with the fly ash or whatever they got it up to the 14.
Yeah.
Think about it. And then also the way buildings were constructed back in the 1980s, even not probably 1990s, they were stick formed or flying formed. You had the big 7.5 yard concrete bucket. You fill the bucket at the base of the building, hoist the bucket up to the top, and then dump the concrete onto the floor. And they're limited to how many square feet they could pour because it was how many trips
with the bucket you could get done.
Get up the building. Probably 86 or 87 when we were doing the 900 North Michigan Avenue building. That one I remember was the one of the first ones we did, pumping the concrete, and that was exciting. They could just pump.
Continuous up it goes.
And that was 9,000, 9,000-pound concrete for the columns, and with floor slabs there were only had to be 4,000.
Yeah,
and that whole technology, the high strength that now. Forget the 11 or 14, 17,000. Oh, we're not limited to height. We can pump it.
Yep.
We can up, 1,000 feet, 1,500 feet.
Were they pumped in stages? I've never even seen how this would work.
What I've heard on lectures for the super talls.
Yeah.
Because I've never seen it, but I think I've heard they have a staging area halfway up or whatever where. The concrete gets pumped up that height. There's some kind of a loading apparatus.
Yeah.
And then they got to have another pump to do the next lift to get it up with regards to going up. I don't know how they're going to do Kingdom Tower, but I know I don't know what it's called now. It's still called Kingdom.
I know what you're talking about.
Khalifa. That's topped out, I think, at 2,000 feet, and then. The last 800 feet is structural steel.
Okay.
But, now we go back to the 70s. Everybody's promoting steel. And there's an interesting piece of trivia, and I think it's still true. Sears or Willis Tower, even though I don't think it's in the top 15 anymore, the tallest buildings, is still the tallest all structural steel frame building in the world. Because you look at all the new super talls.
Yeah.
They're all either all concrete or a mixture of concrete and steel.
Yeah, concrete core and outrigger system or something.
Our Burj Khalifa is, 2,000 feet of concrete and then 800 feet of structural steel.
Wow.
So that whole aspect of the super high strength concrete being able to pump has changed the whole dynamics or how super tall buildings are constructed. And then also the other one, the first buildings that I worked on were all, we call them stick formed. You form your columns, pour the columns. You also form your deck sitting on 4x4s or then steel scaffolding, the deck. And then for the shear walls, same thing. You had the walls framed actually below the deck and framed like a column.
Mm-hmm.
You look at the buildings, everything is almost like an elevator system where everything is climbing up. And another one, when I look at some of the new buildings going up, the safety issues. When I started in the building, okay, you needed a hard hat. And they stick form the buildings. And who cares if stuff blew off the building? I mean, I saw stuff come off buildings.
I bet.
Nowadays, you look at the construction workers, whether it's safety glasses, everybody's wearing vests.
Oh, yeah. Buildings are wrapped, nothing can go anywhere.
and you wrap it, and that's part of the elevatoring system.
The whole wrap walks up. I'm curious, so especially having been at SOM, which is an A&E, and then an E only, do you think the architect-engineer relationship has changed in the 50 years?
Yes and no. It depends how firms work. Like Skidmore has still got the in-house engineering capability. Thanks to and I know him real well, Bill Baker, and but so many of the local Chicago architectural engineering firm have dropped the engineering component.
Yeah,
the big ones in Chicago was Perkins and Will. They dropped their engineering, and other big name architectural firms have dropped the engineering. And I've just talked with one of the an interesting story with regards to Chicago history. You've probably heard of the famed architect Helmut Jahn. So famous architect. Did a lot of stuff worldwide and then in Chicago. His firm started out as an engineering firm.
Really?
Yeah, and then
they
brought him in as an engineer. The engineering component went bye-bye, and now it's his firm direct, and then he hires as a consultant the engineering component.
Wow. Do you think one works better than the other to have it combined or separate?
Well, my days at Benish, interesting relationship, because we were like that with the architect, but we were also like that with the developer owner. And having us three talk to one another when the jobs were starting, there was this synergy that the developer could sometimes kind of twist the architect with regards to, okay, it's this, I want to go this way.
Mm-hmm.
Like I mentioned, the round column versus square column debate. The developer says, I want the square column, and we'll just put drywall around it. So if you can get, and we had this on another couple of other jobs where if the developer can get you as an engineer on board early enough, and the three you can talk, or even four, developer, contractor, engineer, and architect, to work up front as the project is proceeding.
Mm-hmm.
Do what a lot of times nowadays the developer hires the architect. The architect designs the building. Here, engineer, make it work.
Yep.
And the engineer says, we got to do this, we got to do that. And then you have to, it's not negotiation, but it changes the architecture. And then farther along, the contractor comes on board and says, this is too expensive. We got to do it this way. So,
and it just changes. And yeah, it's better together. I mean, in that sense.
The other one I like to brag about that I've been doing for 30 years is talking to children.
Yes.
On how stuff works.
I think that's an awesome.
You can actually find online for anybody watching this video. Type in STEM education, Bob Johnson, and you might be able to find videos of me with regards.
Perfect. We'll put on a link down in the show notes with all the links to your talks and what you had just sent us. And yeah, I think that's a great thing.
And I hope I gave that my fellow engineers, being in the business, should I do it? I lost a lot of hair over here. How the industry has just changed, and I won't be around, but 50 years from now, the stuff that you're currently designing, all the new technologies, that will come on board, whether it's concrete, steel, fiberglass.
It's coming. Well, thank you so much. We'll hopefully talk soon.
Okay, great. Pleasure.
Thank you so much for your time.
Hey guys, thanks again for listening to the episode. Let us know if you have any questions by reaching out to us on LinkedIn, Facebook, Instagram, or email. You can also find these links and more information about the specific episode in the show notes below. Have a great week.